Then our last speaker for this session is Tony Pahl, who is joining us from UCLA, I think.
That's right.
And okay.
Thanks a lot. Yeah, so again, my name's Tony Pahl. I'm a PhD candidate at UCLA working with Alice Shapley. And together with my wonderful collaborators, you can see on the screen, I've been working on this project of measuring an uncontaminated measurement of the escaping Lyman continuum at redshift 3. This paper has been recently accepted to MinRAS of the same title, so please check it out if you're interested in learning more about it. So we've already got some wonderful motivation from this session about why measuring F-escape, especially in lower redshift analogs, is important. But just to give another brief overview here, we can basically model reionization by understanding the ionizing emissivity as a function of cosmic time. So to model the ionizing emissivity, we need to know rho SFR, the cosmic star formation rate density. We need to know psi ion, the ionizing photon production efficiency. And finally, we need to know F-escape, which is the actual escape fraction of ionizing radiation that's produced in these galaxies. So this is the parameter that I'm going to be focusing on in this talk that we're going to be trying to explore. So F-escape is actually pretty difficult to observe directly. So here on the top, you can see a spectrum of a Lyman break galaxy at redshift 3. And highlighted in gold here, I have the Lyman continuum region at about rest frame 900 angstroms. So this is these are photons that have enough energy to ionize hydrogen. So in order to directly constrain F-escape, we want to see the Lyman continuum directly. Unfortunately, as you can see on the bottom plot, the transmission as a function of redshift of the Lyman continuum drops off precipitously past the redshift of about 3.5 or 4. So this makes redshift 3 a great laboratory for studying Lyman continuum directly and seeing which types of galaxies are leaking ionizing radiation. Just a general overview of our current progress of observing Lyman continuum leakers at redshift 3. So one method that's been used to find Lyman continuum leakers is using narrowband imaging. So here's just an example of 4 Lyman continuum detections at redshift 3 using a narrowband filter. Unfortunately, many of these detections have later been found to be contaminated with low redshift sources. So the work that this is pulled from, or the images that this is pulled from, is Robin Bastardi's work in 2015. She actually found 15 out of 16 of the narrowband Lyman continuum detections were contaminated. So this is definitely a huge problem. So just to give a schematic of what foreground contamination looks like, if you observe a Lyman break galaxy at about redshift 3, and you see an apparent Lyman continuum signal from that galaxy, you may follow it up with higher resolution imaging and find a low redshift contaminant along or near the line of sight. It's actually contributing photons that appear to be Lyman continuum photons in the rest frame of the Lyman break galaxy. So that brings me to the sample that I'm working with, which is the Keck Lyman continuum spectroscopic survey. So this is a really deep spectroscopic survey using MOSFIRE on Keck of star-forming galaxies are selected as Lyman break galaxies at redshift 3. So 124 galaxies were observed with MOSFIRE, and 15 of them actually were found to have significant what's called F900 over F1500 out. So just to explain that parameter briefly, here is a composite of these objects in the top here, and I've highlighted the blue region, which is F900, the flux density of the ionizing UV photons from this composite, as well as F1500 is the flux density of non-ionizing UV continuum. And then the out part refers to the fact that this measurement has been corrected for attenuation due to the IGM and CGM. So after taking this average F-escape measurement and performing SPS models to the spectrum, we can estimate an F-escape at redshift 3 of about 9% plus or minus 1%. Also was found using this sample, higher F900 over F1500 is found with greater Lyman alpha equivalent with galaxies, as well as galaxies with lower UV luminosity. So while extensive spectroscopic removal of contamination was performed for these objects, we really need follow-up with high-resolution imaging to make sure there still aren't low redshift interlopers that were missed by the spectroscopic removal. So this brings us to an HST Cycle 25 program, of which Alice Shapley was a PI, and it follows up these KLCS Lyman continuum detections. You can see them in pink in these 5 different fields, together with our ACS and WIFC3IR pointings that we observed these galaxies for. You can also see some non-detections that came along for the ride in these pointings that we can also do this analysis for. So you'll see that we observed in 3 different filters, the V, J, and H filters. And the reason we chose these filters is because these filter sets seem to contain information about contamination. So here you can see a VJH color diagram of some subcomponents. This is from Robin Massardi's work again. And you can see in the upper left, these subcomponents of her Lyman continuum detections that were predicted to be contaminants based on photometric redshift fitting are in the upper left of this diagram, while the confirmed redshift 3 components are on the lower right. And this is really due to where the Balmer break falls in between these filters. So you can see at redshift 3, it's going to fall approximately between the J and H filter, while at redshift about 1.5, it falls between the V and J filter. So in order to look at these objects color diagram, we first need to separate each object into subcomponents to look for those low redshift interlopers. So here's an example of one object that was separated into two segments or 2 subcomponents using source extractor. So now that we have these 2 subcomponents, we can make comparable measurements in V, J, and H and place each subcomponent on the VJH color diagram to see if there's evidence of contamination. So now that we have this diagram, we want to understand empirically which regions of the color diagram correspond to low redshift contaminants. So for that, we use 2 redshift subsamples from 3D HST. So one you can see in blue is built from galaxies with redshifts similar to what would be a low redshift contaminant for the sample. And then in pink, we have galaxies that are similar to our actual redshift 3 spectroscopic detections. So we took these 2 redshift subsamples in VJH color space. We built probability density functions about where the galaxies fall using Gaussian kernel density estimation. So here you can see 2 detection subcomponents are solidly in this blue cloud, and therefore are predicted to be low redshift based on just their VJH colors. So I just want to show the postage stamps of the 13 objects that were confirmed to be uncontaminated. So this is really an unprecedented sample of Lyman continuum detections at redshift 3 as part of a larger statistical sample of the KLCS survey that's both confirmed to be uncontaminated through this photometric method as well as spectroscopically. So now that we have this uncontaminated sample, you can see on the left, we want to remeasure some of the sample statistics from the KLCS survey. So here you can see we remeasure the sample composites or the spectral composites of the sample and reperform that IGM and CGM correction. And we now measure an average F escape of about 6% plus or minus 1% at redshift 3. So this is actually significantly different than the 9% that was originally measured without this removal. Yeah, so to again look at the relationships between escaping ionizing radiation and composite properties, I have these plots here. So the updated composite measurements you can see in green here, as opposed to the KLCS original measurements in red. So you can see F900 over F1500 out is again a function of decreasing UV luminosity as well as increasing Lyman alpha equivalent width. Although the relationships seem to be a little bit weaker in terms of the slope of the relationships. But they're still definitely preserved despite the contamination removal. Another thing we did is we wanted to look at the ionizing emissivity predicted from these galaxies at redshift 3, so without these foreground contaminants being included in the sample. So we basically took the relationship between F900 over F1500 out and Lyman alpha equivalent width. And we took that relationship and assumed a Lyman alpha equivalent with incidence function, as well as a UV luminosity function. And combining these three things, we can estimate Lyman continuum emissivity at redshift 3 from star-forming galaxies of about 5.5 times 10 to the 24 ergs per second per hertz per megaparsec cubed. So this is approximately comparable to estimates of ionizing emissivity from quasars at redshift 3. So even at redshift 3, galaxies are definitely significantly contributing to the ionizing background. So I'll just present a few of my broad conclusions here. So we found foreground contamination, we cleaned the sample of foreground contamination and found 2 out of 15 individual Lyman continuum detections were contaminated. We remeasured that F escape of 6% and preserved the relationship between, and we still found these relationship between F900 over F1500 out, and Lyman alpha equivalent width and LEV, and also found a significant contribution from galaxies to the ionizing background at redshift 3. And I'll take any questions. Thanks so much.
Thanks so much, Tony, for an excellent talk. We'll wait just a little bit, give people some time to ask some questions. All right, so our first question is about the contamination. Rather than just removing the candidates that appear to have contaminants nearby, have you given any thought to actually trying to clean out the contamination in some way?
Yeah, that would be really cool if we could do that. Unfortunately, basically the Mossfire slits is in, it's essentially capturing the spectrum from the contaminant as well as the actual redshift 3 objects, basically simultaneously. So really the separation of the contaminant and the actual redshift 3 object is very small. So it's really difficult to blend that in terms of when you're extracting your 1D spectrum. So yeah, it would be really cool if we could do that. Unfortunately, for the contaminants, it doesn't seem to be possible.
There's another question here. It's a two-part question. I only asked the first part. Sorry, Eric. When estimating the emissivity, do you need to extrapolate the F escape Lyman alpha equivalent with relation? And if so, how do you do this?
Yeah, that's a great question. Yeah, so basically we assume, so we do a couple things. We assume that, we assume the Lyman alpha, the F escape Lyman alpha equivalent width relation continues out to about 55 angstroms in Lyman alpha equivalent width, and then we assume this starts to decrease, basically because the correlations between the source function of Lyman alpha and Lyman continuum, as well as the basically that effect starts to come into play. So we model it that way, and we also we explicitly model this relationship you can see on the screen, F900 over F1500 out versus Lyman alpha equivalent width. And we also include the F escape versus Lyman alpha equivalent width together. So we kind of parameterize those two together to get a better estimate of how that relationship changes. And then, yeah, we do extrapolate or assume some sort of function or some sort of behavior past about 55 angstroms.
Okay, maybe one very quick last question. Did you also try to measure the ionizing contribution separately for low and high luminosity sources?
Yes, we did. So this is so in our paper we have both those measurements performed. So this is essentially the Lyman alpha weighted solution to the ionizing emissivity, but we also did a weight with UV luminosity. So you can essentially see in that calculation that the brighter galaxies contribute very little to the ionizing emissivity, while it's really dependent on the calculation from the dimmer sources. So yeah, that we definitely also performed that calculation. But the number itself is actually pretty similar to the Lyman alpha equivalent weighted solution.
Okay, excellent. Yeah, I think there's more questions that you can go and answer in Slack, Tony. Thanks a lot for your talk.